So today we have the pleasure of welcoming Nina Narodytska, who's done a lot of nice, wonderful research in, well, artificial intelligence broadly, but in particular in MaxSAT solving and various aspects of or related areas to MaxSAT solving. And I think this is what she's going to be telling us about correction sets, core enumeration, and she'll explain to us what that means. So without further ado, please, Nina, the floor is yours.
Thank you, Jacob. Yes, thank you for inviting me. This is work that we published about 3 years ago on a core guided minimal correction set and core enumeration. And this is a joint work with Nikolai Bjorna, Maria Cristina Marinescu, and Molly Segiev. I'll talk about 2 other pieces of work. One that I did with Fahim before this paper and that somewhat led to this paper. And also I'll talk, maybe if we decide to go for discussion, a little bit on ongoing work that we are doing with Nikolai. In general, I'm very interested in the MaxSAT topic and in topic of understanding what the solver is doing. I'm not working on proof logging, but even from perspective of a solver writer, you really want to understand what's going on within the solver, and that's why I choose this topic to discuss with you. Okay, let's see. So one slide about myself. So I'm a researcher at VMware Research. I did my PhD in constraint programming, and I worked at MaxSAT and QBF, mostly on writing solver side. And recently, maybe last 3 years, I'm mostly working on verification of ML models and explainability of ML models, and on MaxSAT as well. But today I won't talk about ML models. I will be focusing on MaxSAT. So here's outline. So first I'll give a background on the topic, and then the first part will be on analysis of solvers, at least the ones that we know and we published. And then I'll talk how this analysis can be used to perform correction sets and core enumeration. Yeah, and you can stop me at any time because it's a really informal talk, and like if something is not clear or if I try to do a lot of examples, but because they somewhat simulate what the solver is doing, it might be confusing. So we can actually, but they're actually all very simple. So if something isn't clear, let's stop and go step by step so we are all on the same page. Right, so I'll start with very basics that we're on the same page. So we have a Boolean formula, we have set of clauses and set of Boolean variables. Each clause is a disjunction of a variable, its negation. So we have not for negation. So we have 3 clauses there. And solution, the goal is to find a solution that satisfies all the clauses. So if we have a solution, for example, x1, x2, and not x3, then you see that at least one literal in each clause is satisfied. By the way, do you see my pointer?
Yes, we can see your pointer fine.
Great. Right. So, but in many cases, there is no solution. So we have a formula, for example, as you see here, and just there is no solution here. So you can actually check. It's very simple because C1, C2, and C3 implies that all X1, X2, and X3 must be true, and none of the other clauses can be satisfied. But if you're given an unsatisfiable formula, you can just return unsat. But maybe a user might not be happy with this answer because maybe it's unsat, but there is a solution that satisfies most of the clauses. Like what will have almost solution? That's lead to development of MaxSAT and dealing with unsatisfiable Boolean formulas. So in maximum satisfiability, we talk about unsatisfiable problems. And as I explained, we will allow to violate certain clauses, right? So, but usually in a somewhat general formulation, you have clauses that you really don't want to violate. So those are hard clauses. And you have also soft clauses. Soft clause is those you actually can violate to obtain a solution. But violation comes with a cost, and every soft clauses usually is associated with a weight. And this weight, in the very basic definitions that we will be looking now, we will pay cost 1. If you have a solution for each clause you violate, you pay cost 1. In more general formulation, you might have weights, so they don't have to have all weight 1. And now we want to find an assignment that minimizes the number of violated clauses. So consider an example. So let's say we have an assignment not x1, not x2, and not x3. So it must satisfy all the hard clauses because it's a requirement. We are not allowed violation on the hard clauses, but now all the 3 soft clauses are violated, and we pay cost 1. So that's why cost of the solution is 3. So consider another example. So we have x1 is true and not x2 and not x3. So in terms of the violation, as before, we do satisfy all the hard clauses because we have to. And now we violate 2 soft clauses and 1 is satisfied. So we have cost 2. So you see that different assignments give you different costs, and the goal is to find the one assignment that actually gives you the minimal violation cost, minimum violation cost. Right. So this is one view on MaxSAT. So you kind of try to do your best to find the solution that gives you a minimum amount of violation. But again, from the user perspective, there is another view on unsatisfiable formula, because MaxSAT is dealing with unsatisfiable formulas, right? So if you have unsatisfiable formula, there are additional notions that people suggested to explain the user or the solver why the problem is unsatisfiable. So the first, this is 2 main notions: unsatisfiable core and correction set. And usually we are talking about minimal unsatisfiable cores and minimal correction sets. So that's why these abbreviations you probably saw in many papers: MUSES and MUSES, minimal unsatisfiable set, and MCS at minimal correction set. Right, so unsatisfiable set. So in this case, we treat all soft clauses as hard clauses, and it's the same in the SAT solver. It's a subset of clauses of the formula. When we treat all soft as hard, that already enough to obtain unsatisfiability. So if we look at C1, C3, and C4, you see that together they give already unsatisfiable formula. So it will be an unsatisfiable subset of unsatisfiable core. And it's minimal as well, because if you remove one of the clauses, it becomes satisfying. Correction set, it's a dual notion in a sense. Correction set, it's a subset of clauses. And now we're talking about soft clauses. So it's a subset of clauses that if you remove them, the remaining formula becomes satisfying. So consider our example. So if I remove C1 and C3, and this is all clauses that I left with, hard clause and 1 soft clause, this formula is satisfying. So it will be C1 and C3 is example of a correction set. But clearly there are many, right? So for example, if I remove C1 and C2, again, remaining formula becomes satisfying. So you can see there are many correction sets, and those are minimal that are possible. So this leads to another research direction in MaxSAT, or not necessarily MaxSAT. MaxSAT is what we were using, but dealing with unsatisfiable formulas. How many minimal course and correction sets are there in unsatisfiable formula? So you see there are kind of, if we summarize the background, there are 2 main research direction of analysis of an unsat formula. The first question that we can ask: what is an assignment that minimizes the number of violated clauses? Or also in other words, what's the optimal solution of a MaxSAT formula? And another one, which seems to be somewhat related, but not maybe immediately clear how, is how many minimal course and correction sets there in the formula. So there are two research directions on counting and on finding the optimal solution. And what we done in this work, we said, okay, so let's look at the first question. Let's look how the MaxSAT solvers work to find this optimal solution. So what we trying to understand as solver progresses, what does it learn about course and correction sets of original formula? And it's somewhat a byproduct of the execution of the solver. But what we are saying is that, okay, as solver progresses, and it does have this information, at least some pieces of this information, can we use it to perform enumeration? And this work was exactly about that. So how we can use execution of a standard MaxSAT solver to analyze what it's doing and what kind of a byproduct of the execution, extract additional information and perform enumeration.
And then you actually want to list these core sets, say, or correction sets.
Yes, this method, they explicitly list of them. It's not just a number. Mm-hmm. It's exact, and also at the end it lists them. And of course, as you understand, it may be huge for some problems. So from enumeration point of view, you do the best you can. Right. Okay, so this was a background, and now we'll talk about analysis of core guided solvers. This is work that I've done with Fahim, for that, first I need to explain what actually core guided MaxSAT is doing, so that we can analyze what it's actually learning about the original formula. So let me briefly explain the main workflow for MaxSAT solvers. So we start with a formula when we have psi and delta clauses. Let's say psi is soft clauses and delta hard clauses. And we'll be working with a SAT solver as an oracle. So in the beginning, core guided solvers, they become very optimistic. They're saying, okay, let's assume that all soft clauses are hard clauses. So I can satisfy everything. And you just get a formula, standard SAT formula, and you give it to a solver, SAT solver. And there are two possible outcomes. Maybe it's at SAT. In this case, you're lucky, and then you find a solution because you treated all soft clauses as hard clauses. So you have a solution for entire formula. Or you might get unsat. And in case of unsat, you get a core, unsatisfiable subset of clauses. Then all the core guide solvers, even details are different, but general idea is the same. So what they do, they take the formula, soft clauses, and they get this unsatisfiable subset Mi, and then they transform the formula. So they go from psi I to psi I plus 1. And the difference is that psi I plus 1, it's a relaxed version of psi I. And I'll explain in a few slides what exactly is going on. Then we just repeat. So in every step, we do relaxation. And at some point, we relax formula enough so it becomes satisfiable. So this call here will return SAT. And when it returns SAT, we are done. And we know by correctness that it terminates for, remember that we are talking about the formula when we paid cost 1 for each validated clause. So in this case, it terminates exactly in optimal of the solution number of steps. So if the optimal is 5 for the formula, it will terminate in 5 steps. All core guided solvers work under this simple loop. The difference is how the transformation is performed. And we will be looking at the transformation that uses cardinality constraint in the very basic formula. So it was proposed in 2006, if I'm not mistaken, by Fu and Malik. So basically, the relaxation is performed through the set of formula relaxation and additional cardinality constraints. So on top of the hard clause, we'll be adding cardinality constraints. How it works. So we will now consider this relaxation step for Malik algorithm. So here's our example. So we have a formula. This formula has 5 clauses. oh, sorry, five cores, but eight clauses. So you see you have this from C1 to C8, and these boxes that I draw, they represent cores. So we don't care what the hard clauses are here. It just, we will be focusing on the core structure. So let's say that hard clauses implies that C1 and C3 form a core. So together with hard clause, it's formed as unsat. So we have another core C2, C4, and we have five. Basically, we have five cores. Yeah. So if picture is not clear, please tell me. But hopefully it's clear. So it just says that we have a formula with 8 clauses, and we have 5 cores there. So suppose we find, as the algorithm progresses, we find the first unsatisfiable subset, which is C3, C4, C5, C6, C7. So this dark blue core is the first that we find. The relaxation does the following. For each clause, it introduces additional fresh Boolean variable. So for C3, we introduce B3 and so on. So we have this relaxation now. We introduce cardinality constraint that says that exactly one of these BIs equals 1. And now we relax the formula. So we take previous clauses out and replace them with the relaxed clauses. So hopefully you see that the formula was relaxed, right? Because before in the original formula, we were requiring C3 to C7 to be satisfied, but now one of them is allowed to be violated, but exactly one of them, because cardinality constraint ensures that only one can be valid. Right. So
and again, just to clarify this, we're doing all the clauses that we see here are the soft clauses, right?
But
because the hard ones, we would never allow ourselves to violate those.
Yes. So usually when you say that when MaxSAT is going through the loop, when you get an unsatisfiable core or satisfiable subset, usually never talk about hard clauses because they are there, right? But you can't relax them. Right, because that's why it's a bit confusing. On its own, they might, if you have hard constraints on its own, this clause might not form an unsatisfiable subset, but it's easier to only talk about soft clauses because hard clause we won't be able to relax.
Okay, thank you.
So one question that we ask here, and this is the work we were doing with Fahim, like we will have this loop and solver will progress and formula will change. And course on this unsatisfiable subset that we will be obtaining on each step, they will be changing, right? So for example, the unsatisfiable subset that we find at maybe step 5, it won't be really a core of original formula. So what is the question here is what is the relation between this unsatisfiable subset that we will be finding as we progress and cores of original formula? Because now we will be talking about two notions. We will be talking about unsatisfiable subsets that we will be getting through the execution and cores of original formula. I found now that it's easier to call this unsat subset metas. Otherwise, everything will be a core. So we'll call meta unsatisfiable subset that we will be obtaining at each step of execute on this loop. And cores, we will be only refer to cores of the original formula. Right, so the first thing we've done, we thought about it. We said, okay, solver works, it progresses, it keeps giving us this relaxed formulas and metas we will be obtaining. So how we can relate them, metas and cores of original form. Let's look at the example. Maybe, hopefully I didn't mess up the example, but what I'm trying to illustrate in this example is that exactly this point, as you progress, unsatisfiable subsets changing. So we start with the same example when we have 8 clauses and 5 cores. Let's consider the first iteration, we find exactly the same meta. Now we call it meta, but in the first iteration, it exactly coincides with one of the cores of the original formula. So we relax it as before, and this is our new formula. So we have all the clauses that were part of first meta are relaxed. We have a cardinality constraint, and some other clauses just stay there, right? This is how the formula looks after the first step. But what about cores? So you can actually see that if you try to look, let's say look at C1, C3, that was a core of original formula. Now we have C1, C3, B3. This is not a core, right? Because if I consider these two soft clauses and hard clauses and cardinality constraint, I can relax C3. So this is not the core. So here, two cores at the left, right? So, if you maybe run or work on MaxSAT solvers, you will core guided. We were talking about only about core guided solvers. I will not every time repeat the core guided solver. But if you work with MaxSAT solvers of this type, you will see that this meta, that unsatisfied subsets are growing. And this was going on, right? So in this simple example, you can see that now we have like a bigger unsatisfiable subsets or bigger metas. So suppose the next unsatisfiable subset meta is the light blue one here. So again, we get the meta, and then we relax it, and this is our new formula, right? So we again relax formula one first. What is the cores? So here, because I choose this example to be very simple, this green one stays, right? Because none of the clauses in this green rectangle was relaxed. So you don't need to understand all the details here. We can, if we go to discussion, we can go on this example again, but the point was to demonstrate that cores are changing. And they become, and this is partially why I choose to call them meta, because they're somewhat aggregating. You can see from these pictures that they're aggregating cores of the original formula.
A question, could card also be part of a meta? I could take cardinality constraints.
They're hard. Oh, wait. Okay. If you're talking about RC2 algorithm, MaxSAT algorithm that treats cardinality constraint as soft clauses, maybe in this case it's a separate story. But in the vanilla algorithms that I'm describing now, hard when you add cardinality constraint is part of the hard.
Okay.
But you're right that there are algorithms that treat cardinality constraints as soft, and then things might be different. Right. So cores are changing, and this was the main question we asked: what is the relation between metas, cores of the relaxed formula, and cores of the original formula? To give the result, I need two very simple notations. So let's say we have a clause C at some point of the execution, and the original clause was C1 and was relaxed twice with B1 and B2 at some, also again at some point of the execution. So we have a relation that returns the number of set of relaxation variables per clause. So when you say rel of C, you get B1 and B2. And in other notation, original of C, it's just original clause. So two very simple. Okay, this was the main result. So if you find, you look at the card, so all these cardinality constraints that you introduce, and you get a solution. This point that we are looking at the point just before the relaxation. So you get a solution of card constraints for a given meta. And you consider the following projection. So basically you take this solution, and then you collect all clauses in meta that didn't get one, so that didn't get any variables relaxed, right? So you have CJ has each of these clauses might have relaxation variables. But in this solution, they're all set to 0. So the result is that this projection I minus of meta is a core of original formula. Let me explain the example. It will be more clear. So again, we do this operation right before the relaxation. So come back to our example. It's a step. It's step after we just found the second method. So this is our second method. And this point, because the point before relaxation, we have one cardinality constraint. Now let's look at the solution of the cardinality constraint. So we have 3 solutions. So usually 0, 0, we don't consider, but here, just for the purposes of example. So we have B6, 0, B7, 0, right? And something else is 1 with respect to the cardinality constraint. We can have B6 is 1 and B7 is 0, and B6 is 0 and B7 is 1. So we only have 3 solutions. So let's see how it performs the relaxation with respect to this matter. So if B6 is 0 and B7 is 0, so this one is 0 and this one is 0, then we just get a set of 3 original clauses, C6, C7, and C8. And it's a core of original formula. We're not talking about minimum cores, it's just a core. So you can clearly see it's a core of original formula. It contains multiple cores. If we look, for example, in solution B6 is 1 and B7 is 0. In this case, so you see if B6 is 1, then this clause is gone, right? And B7 is 0, so literal is gone. We get C8 and C7 as a projection. And you see that's exactly the core of original formula. Is it clear? Or not so much? I know this is confusing maybe a little bit, but actually it's simple, but because we're talking about 2 unsatisfiable subsets, it might be a little bit tricky.
I mean, it seems in the second step it's always somehow after the first relaxation, you'll either get a core or a union of 2 cores.
Right, union of 2 cores, or you might get still core of original formula, depends.
Yeah. But after after I steps, you'll get a union of 1 up to I cores.
Right.
And then you're somehow using setting these relaxation variables to project out subsets
right.
that are also cores somehow.
Right. Okay, let's maybe go again, because why this is actually, this core analysis is my main motivation for this work, and I guess my main interest here to understand what's going on. So, okay, we have these methods that we are getting, right? And we have these cardinality constraints that accumulated as we go. In a sense, the knowledge of the MaxSAT solver is in this relaxation and cardinality constraints. It's what it learns. This is what adds to the formula. And now we are trying to look back, right? So we're in a certain stage, we're here. We have only 1 cardinality constraint at this point, and we have a new meta, M2. Now I want to take this meta, and I know that it somehow, or I suspect that it somehow accumulates a course of original formula, but in which way? So in the way is very simple. If you consider solutions of cardinality constraints and see how this solution is somewhat projected on this meta. So let's look at the same on this solution. B6 is 1, B7 is 0. It's a solution of meta. Well, it's a solution of card, right? So clearly, because 1 is 1 and other is 0, and the rest is 0 because they're not even relevant to this meta. Now you see, let's look at these chords here, right? So this clause is gone because B6 is 1, and B7 is gone because it's 0, right? So what's left? C7 and C8. And this is guaranteed to be a core of original formula. So you can look at all the solutions, all possible solutions of cards, and it will always hold. It does look a lot of results when you're trying to prove for these executions. Sometimes might depend. There is an execution, then something happens. But here, it's this result doesn't depend on the execution. It's always holds. You can consider all the solutions. You can you look at these projections, and they always course of original form. So if we look, let's say, let's look at the last solution. So in the last solution, B6 is 0, B7 is 1. So let's see what's going on. Because B7 is 1, this clause is gone. B6 is 0, the literal is gone. We have C6 and C8 left in the projection. And this is exactly the core of original formula. Is it clear? Not. Okay, this is very high messages. You look at all the solution of cardinality constraints you accumulated. You do the projection as I described before. So you basically only look at the clauses in a meta that didn't get one. So they were not relaxed. What's left is the core of original formula.
Mm-hmm. Yeah.
Right. So again, this was our main result here. So even this course and these methods are changing, and they look bigger and look different, but we're still using these methods. There is a still way to extract course of original form. And at that point, we didn't continue working on this for him because it's somewhat a messy topic to work on. Where solver works, things are changing. But we got this result. There are a few other results, but they're all based on this, the one that I explained. And if we want to discuss, we can, the work that I'm work in progress, I'd say, with Nikolai, we try to dig a little bit deeper. Like we get this course through this solution enumeration procedure. What are actually characteristics of this set of course? For example, what is the minimum correction set, or the main things that we want to prove, and I think we did prove that. So let's say you run the solver, right? And you keep using this procedure that I just described, you keep extracting course of original formula. We don't, at this point, we don't care how expensive is it, but we just execute the procedure. Every time we get a meta, we run through all the solutions, and we get course. And then when solver terminates, we, as a byproduct of this procedure, we will have a set of course of original formula. So if minimum correction set of this course that we extracted is equal to the optimal solution, we have alternative certificate for unsatisfiability, right? Because we have a set of course of original formula, and we know that minimum correction set of this course is equal to the optimal solution. So in a sense, I don't know, maybe Stefan, it's maybe more interesting to you. In a sense, it's a certificate. It's a proof why the optimal solution of MaxSAT is K. Let's say if it's K, then the minimum correction set of all this course, or you can talk about minimum heating set, it's the same thing in this case, is also K.
Yeah, but you need like to show that the heating set is minimal also, right?
Sorry.
You need to show that the correction set is minimal also. Like how do you know that you actually have a minimal correction set?
Well, suppose if you procedure. So I give you a set of course, and let's say you have an oracle that tells you that, and we trust this oracle, let's say, that minimum heating set, which is the same as the minimum.
Yes, but sure, then we are fine, yes.
Right, yeah, so there is, it's a, maybe it's not a way to, yeah, I agree that it will be another procedure to prove, but it definitely will be alternative certificate, because usually when the solvers are just terminate, you rely on the correctness of the solver.
Yes.
So I have I'm sort of maybe going off in completely the wrong direction, but so Because there's this other approach also, the implicit hitting set solvers, right? Where you
Right.
actually only extract cores from the original formula.
Right.
And which I guess is considered to be, well, they're orthogonal, but somehow I got the impression that implicit hitting set solvers are better if I have to choose. Or that's a complicated question, maybe. But the question I'm getting to is this: it seems like, sort of, suppose I love implicit hitting set solvers, but I want to initialize, like I want to find cores quickly. So it seems like I might run core guided for a while and collect these metas, and then I can play around with card and like
this was my
like original cores, and then at some point decide, okay, now I'm going to switch to implicit hitting set or something.
Right. Okay. Okay. To be fair, Jacob, this was I started to look at the competition this year a little bit, and I saw that hitting set based solvers are winning. Right. Well, we have to be careful with the word winning, because it's not like they're just killing. At least for unweighted, I was looking at unweighted. They do solve more than core guided, but the core guided are not under. Not many people are now pushing for core guided, right? And then I was kind of puzzled, like, why is it going? What's happening? What core guided solvers are missing that hitting set MaxSAT solvers have in their tools. And this also kind of led me to look to dig more in this case and analyze these executions and methods, because what I want to show that actually core guided solvers, they're doing in a sense implicitly very similar thing what hitting set solvers are doing. They're also extracting the same core structure, but implicitly. So they learn the same core structures, they just don't output maybe. And also my hope is if we understand better what kind of this core certificate is getting, maybe we can see what is exactly the deficiencies of core guided. Maybe they learn too much, because, right, so to get, you don't need all cores. You only need enough cores so that the minimum hitting set or minimum correction set, in this case the same, is optimal solution. So it means that, as hopefully will show that they also extract this core certificate, maybe they're not efficient, or maybe they look at too many cores and many of them are useless to prove the optimum. And know that for hitting set based solvers, they also have the same problem. When they try to extract next core, they're not guaranteed that they will push optimal. This is their main problem, right? Because the way they work, they might get a new core of original formula, but it's useless in a sense, or maybe we don't know whether it's useless or not after all, but the good cores for them, good set of score for them, the ones that push the optimal, the low bounds that they have. Right, so they're also facing of the problem, what is a good course to extract. But what I'm looking now, I'm trying to understand what the solver is missing, what core guided they're missing. And frankly, I looked at this benchmarks that hitting set solvers are better, and some of them actually can be solved by Gurobi. Right, so it's a small problems. They have a small number of variables and small number of clauses, compared to to large formulas, but they have many cores, many cores. And for core guided, for example, to prove that meta is unsatisfiable subset, it has to go through the whole solution of the cardinality constraints and prove that this projection is a core. So when you have many cores, it somehow sometimes also, but I don't have a clear answer here, but I did see that there are classes of problems where core guided are just losing or badly losing to hitting set based solvers. And those are problems with many interleaving cores. When I try to print this course, this is what I saw. Anyway, so we can continue. Yeah, so I'll talk about, I have 15 minutes left. Yeah, I'll talk about the enumeration procedure. So we published it at the CHKI a few years ago. Now we will be looking at MaxSAT solver. All what I'm talking about, I was talking about MaxSAT solver and one execution of the MaxSAT solver. But now MaxSAT solver will be just a block of a bigger framework that has 3 steps: relax, strengthen, and heating set duality. So the first step is relaxation. So here we have the first step. It's just take a formula, which is a satisfiable formula, and solve it with the MaxSAT. And at the end, when we know and MaxSAT goes through the sequence of relaxations, you will get, as an output, you will get satisfiable formula. So this is what I was talking about now, about this loop that you get unsat, you go relax, relax, and then you get a sat. Right, so it will be one block now. So first we run MaxSAT. Then, because formula is satisfiable, we go to the strengthening procedure. We block all the solutions. So if you block all the solution of the formula, it becomes unsatisfiable, right, naturally. And you repeat. So this is the main loop. And then you will terminate. So you will continue in this loop, and then you terminate. After the termination of the of this procedure, we will have all the minimal correction sets collected, and we will have some minimal course correct, but not all. So the rest of the course that we missed, we will go through this heating with additional step of through the heating set duality to collect cores that we missed. And there are the relaxation strengthening framework was proposed before us. It was only dealing with minimal correction sets. So we did 2 enhancements. So we did the Mcs extractor. So in the original work by Joao and John, I think, sorry, somehow I had the reference, but maybe I deleted the slide. Yes, so we enhanced it in 2 ways. So first we add this course extractor, and second, we find a procedure which is more kind of a heuristic way how to extract correction sets quickly. I will explain next what's going on.
So we start with just to go back, this relax strengthen loop, what are we, sorry, a very basic question. We're trying to find all, are we listing all like optimal solutions to the MaxSAT problem here?
On every step, yes, we will be listing all the optimal solution on to the MaxSAT and on every step, on every loop iteration, and then we are guaranteed to get all minimal correction sets.
Mm-hmm.
All the solutions.
But we're like, I mean, the first round we see what the best MaxSAT solution is,
yes.
and then are we going to look for equally good solutions in the second round, or we're like?
No, whatever is next. So let's say all the minimum very first round. Let's say you have a minimum correction set of size 1. Suppose you found all of them, you block. Maybe now you have a new formula. It's a satisfiable formula. You don't know, but maybe the next minimum correction set of this already formula with blocked correction sets of size 1. Maybe it's 5. Right? Mm-hmm. And then you solve it, and then you enumerate all the for this formula will be again minimum correction sets, and they will be of size 5, but they will be minimal for original formula and of size 5, and then you keep doing it. So you basically enumerate minimal correction sets by cardinality.
Mm-hmm. Ah, okay.
Right. Because you find all the correction sets of size 1, you block them. You say, okay, now you can't have them. You just forbid. New formula. Then you get next set of corrections, minimum correction sets, block them, and so on.
And right. When do we wait? So and when do we terminate this?
So at some point, wait. Okay. So termination. I think when you will add blocks, and those are hard, and then you have a hard set of hard constraints, and then there will be unsat. All these modifications and all these blocks, there will be hard constraints, and at some point you will get that, okay, the formula has no solutions.
Okay, makes sense. Okay, so okay, you're adding hard constraints, so like this has to be a finite process is basically what you're saying. Yes. Makes sense. Thanks.
So heating set duality, if you're familiar with heating set based solvers, it's the main theorem to run. So, okay, heating set duality, okay, why we are doing it? It's exactly what we discussed with Jacob now. The moment you terminate, you guarantee that all minimum correction sets are enumerated. It was shown by Ja and, I forgot the thing. Yeah, so by Ja and co-authors in their paper. So all minimal correction sets are enumerated, but the framework, what we are doing doesn't guarantee that all minimal cores are enumerated. So that's why we're using this heating set duality. So suppose you are given all minimal correction set of the formula, you're given to you, and we know that we have them at this point. So minimal heating set of all muses is a minimal core. So consider an example. So you have a formula with 4 clauses, C1, C4, and we have 2 cores, right? So consider what are possible minimal correction sets. So one correction set, because there are 2 disjoint cores, right? So one correction set is C1, C2, because if I remove these 2 clauses, the formula becomes satisfiable. There is another one, C3, C4, and 2 more. So these are all minimal correction sets, and we are guaranteed to have them after this step 2. Now, to enumerate all the minimal cores, we just need to look at the heating set of those. So for example, this is one heating set, and this is another heating set. And this is exactly course of original formula.
The fact that we have all the minimal correction sets when we terminate, I mean, are we supposed to like immediately see this, or no, this was like a paper?
Yeah, this was a paper that Ja had with co-authors. They didn't do anything with the course, but they proposed to use MaxSAT to enumerate all the minimal correction sets. Because when you do this, look, you have correction sets, minimal, you block them, right? Then you have to find all the next size minimal correction sets, and so on. Okay, so if it's not clear, then we need to look at the proof to have all the details. But the invariant is that after the algorithm terminates, we know about all minimal corrections.
Okay.
Right. So basically, this step 3 that we added, it's kind of a cleanup step, because we know that we can enumerate all the cores. So, and we do have to do it. That's why after we, and you know, there is no, I don't think there is any algorithm that can guarantee to enumerate all the minimal cores if we are not using this heating set duality. Like, let's say I want to enumerate all minimal cores, right? There is no algorithm that does it directly. You can enumerate all the correction sets, and then through the duality, you can get cores. Or in this framework, we are getting some cores and whatever we can, and then through the heating set duality, we complete the set. But I don't think there is an algorithm that does it, you know, like not using the duality. I might be wrong. Maybe there is something now. Okay, so this is one of the enhancements that we propose to the procedure, because in this procedure, when we block solutions, we block minimum correction sets. And it's somewhat expensive, right? Because you have to find a solution, you have to block, next solution you block because you have satisfiable formula. So you go through the solution and you can have a lot of solutions. Even if we don't care about efficiency, you can do it, doesn't matter. But if you do care about efficiency, it's not fast, to be honest, right? So that's what we proposed, a simple trick, which surprisingly worked very well. We called it Mcs Rotation. And again, we use this property here that all solutions are, that we obtain here are minimum corrections. Okay, so this we discussed a little bit with Jacob that this framework produces correction sets, but there is additional property that they're all in the order of non-decreasing cardinalities, right? So first we find solution set of size k. When we block them, we find solution sets of size k plus 1, but k plus 1 guaranteed to be greater or equal, no greater. It's still, if you go to the next loop, it will be strictly greater than k. Right, so in the first step, we might find all the correction sets of minimal correction sets of size 1, maybe then 2, maybe then 4. We don't know, right? It just, but what we know for sure is that cardinality will grow. Now, in this paper, we proposed a fast procedure how to find these correction sets without. I'm almost out of time. Okay, I'll maybe explain this and people.
That's fine. I mean,
okay, let's just stop. Right. So what's the procedure? Okay, consider a formula: five clauses from C1 to C5. Right. So this formula has correction set of size 1 and 2. Maybe see, but we only will focus on 1 and 2. There is only one correction set of size 1. And there is a corresponding solution. So solution would be not x1, not x2, not x3. It's enough to satisfy 4 clauses, and 1, it will be correction set, right? So we have a correction set of size 1. So after that, we will block it. So we don't allow the solution anymore. And then we'll go to the second round of the loop. So we'll be looking for correction sets of next size, and next size will be 2. So we find the solution, we run SAT solver, we relax the problem, we had a SAT now, we run SAT solver, we get a solution. So solution, let's say it's x1, not x2, not x3. It's enough to satisfy 3 clauses. So we have a minimal, we guaranteed, because it's a solution of the formula, we guaranteed that C4 and C5, it's a minimal correction set, and we write it down. The standard procedure would be to find the next solution of the satisfiable formula and block it. But let's try a very simple trick. We take the solutions that we had and we flip one literal. So we flip from x2, not x2 to x2. So it's exactly the same solution, but I just flip. So what's happening then? So we got that, and we again managed to satisfy 3 clauses, right? And 2 are not satisfied. So we know that it's a correction set. At this point, we know it's a correction set, but we don't know whether it's minimal or not. So the question is whether it's a minimal correction set or not. Let's do another flip. So we take, because we can do this flip as much as we want, right? So we had this I2, now we try I3. So we flip on the third variable. We go from not x3 to x3. Now all of them are positive. We satisfy 3 clauses here. 2 are not satisfied. Again, it's a correction set. We know this because this solution, it's a certificate for this correction set. But again, we don't know whether it's minimal. You see, we can, for size 1 or 2, it might be obvious that you can check. But if you're at some iteration of the algorithm, and now you're finding correction sets of size k. With this flipping procedure, you flip, you get a correction set of size k. How do I know that it's minimal?
But didn't we already block off all these smaller correction sets?
Yes, but I don't know whether any of them is a subset of what I found, because I just got it by flipping.
Okay. So you need to check if it's a subset of what you already have. Yes.
Yes, exactly. That's what we did. So, yes, there is nothing like very deep here. So we collect all the sets, correction sets of size 1 and 2. Whenever we get a new, there are two points here that we have to be lucky. The first luck point, when I flip literal, I don't even guarantee to get a correction set of size k, the k that we are looking now. In some cases, I flip and I get a correction set of size, number of unsatisfied clauses more than k. Then I just throw it away, because about this guy, I can't say anything. But if I am lucky, if I flip, and now I'm looking at correction sets of size 2 and I get correction sets of size 2, at least it's a good candidate that it can be minimal, but might not be. Right, so that's what we are doing. We are collecting these collection sets, and we know that we didn't miss anything because we are going by increasing cardinality. So we collect them when we are lucky by this flipping procedure. We get a correction set of the size that we care about, that we are looking right now. We need to do this subsumption check. We need to check whether there is a.
I'm still a bit confused. Like, this depends a bit, I guess, how you encode things and how you like run the solver. But when at the point where we block off C1,
yes,
like this blocking of C1 make sure that we will never find another correction that contains C1?
Exactly. If I go through the solution of the SAT formula. So if I will be going here, during the blocking procedure, if I find solution of SAT block, but I don't want to finding solution of SAT formula every time.
No, but you do this flipping, but like you don't, you need to check if this is a solution anyway, right? But you're saying you're just checking if it's a solution of the original formula. You don't check if it's like a solution of the formula with blocking off stuff and like the corresponding extension variables and stuff.
Right. So this is a solution, right? But I don't know whether you're saying that we might not even wait. Maybe there was a bug. Okay, I need to think about it. I think what you're saying is that I could just check.
No, maybe not, because you would then flipping one thing is not enough. If I understand correctly, like what you do is you flip one of the X variables and then you check if it's satisfiable with respect to the original formula, right?
I check how many clauses are violated.
Yeah, but in the original formula.
Right.
Like you don't look at the rewritten stuff.
Yeah, I only look at the original formula and see how many of them are violated.
No, yeah, then you wouldn't know if you had C1 already, yes. And I guess the problem why you might not want to look at the rewritten formula is because then you would also need to usually do this by having
but I need to extend
activation literals. Yes, you need to extend for the new variables, and then it gets more complicated. Yeah.
If I need to show that the solution of the original form or on the modified formula is the same as the finding, because I don't know if it's a solution or not, right, of the modified formula. I'm only looking at modified formula has a lot of additional variables and cardinality constraints and everything.
Yeah, right, exactly. So like you would,
I work on original formula and only original variable. If I would go, I think you're right in the sense that if I have a quick way to check whether this flipped guy is a solution of the modified formula, it will be also one way to check. But formula grows, as we do these loops, formula grows. So it's not cheap. And it might be of course a side effect of the benchmarks that everyone is using for current correction set enumeration. But I was getting huge amount of correction sets very quickly. because you see, it's like a recursion, right? So you flip, you go in. I don't know, my program was crashing. How deep was my how many flips, and I was getting like millions, of course, very quickly. Of course, as I said, it might be fact that how this benchmark set might be not optimal or something, but for this benchmark set, it was working extremely well. It was very, very fast. Right, so I was collecting all this correction course, and whenever I get a correction set of a size that I'm looking at now, I did the check, and in this case, you see it's a simple example, but you can see that none of the course that minimum correction sets that I found is a subset of our candidate. So then yes, it's a minimum correction. Okay, I'm almost done. News extraction procedure is basically, I already explained it here, like when I was talking about the core analysis, how we were extracting newses. One may be interesting, or maybe I should finish. If someone want to go, just go, and then I can explain a little bit some adjustments that we did to the news extractor, which is quite interesting. But yeah, experiments. I will quickly say about experiments, but I want to tell you that it's not the main point now, because yeah, maybe now even 2 years past, maybe there are much better algorithms for correction set enumeration, and even there back then we were not the best for core enumeration. But what I like about this approach is different, right? So we're trying to get it as a byproduct of a MaxSAT solver run, and it also gives us helps us to gain understanding of what is going on. So we did enumeration of correction set and course and only correction sets because it was actually the fast one. So we compared with Markov, which is a very well-known algorithm for course and correction set enumerations. So the standard diagram. So the higher in this plot, the more points you see above the x equal y line, it means that better our algorithm works. We called it Flint. So for correction set enumeration, we were much better than Markov, you see, because there are more points here. For course, well, it's hard to say, like we were a little bit, for Markov, we were a little bit better. And if we drop core enumeration, so because it's costly, we were even better because it's all done within 1 hour. So within 1 hour, we could find even more correction sets. And then we compared to
sorry, these plots are the number of like course forms, not time.
No. Yeah, time is 1 hour.
Yeah.
Sorry, I didn't explain it. It's so in this experiments we give solver time 1 hour. Each solver get 1 hour, and then as much as it can report. So that's why this x and y x is about the number, right? And yeah, at that point we compared to everyone, and in terms of correction sets enumeration, we were much better because we were so cheap. You just flip, and you kind of by luck you might get something which is a correction set, minimal correction. And in terms of uses, even 2 years ago we were not the best. There was another algorithm, MCMUS by Fahim and George, and it was already beating us at core enumeration. Yeah, so this is end of my talk. So what I presented as a start is the motivation, saying that we want to gain better understanding what core guided solvers are doing, and my additional motivation now to understand what they're missing that heating set solvers have and outperform core guided solvers in competition, at least now. Again, it's given the set of benchmarks, but nevertheless, they do outperform. Partially, this work brought us to the enumeration framework, that we look at what MaxSAT is doing and see how we can use it to perform enumeration. And what I'm interested now is to get even better understanding what is the connection between these metas, this new unsatisfiable subsets, and course, which is an unsatisfiable subset of the original formula. Yep, thank you.
Like one question I have is like, if this flipping is so successful, couldn't you just run some kind of local search? But I guess then the problem is that you don't have this guarantee to like have all smaller MCSs already or something.
You mean local search just outside of the framework, or run local search somehow on one of the iterations? If you just run it, then it's tough because you will start getting these correction sets and you have to minimize them. Minimization is expensive.
Yeah, right. So I guess you would need to run it inside and only be interested in like a certain size until it gets hard, at which point you run the solver to completion to like find all or something. Yeah, I see.
So what we are doing is exactly local search in a sense. What local search is doing is flipping literals.
Yeah.
But I only flip, but my neighborhood is of size 1. But even with a size of 1 of neighborhood, it was successful. I was actually very surprised how efficient, because there are so many small cores, so many. You can get like up to million of cores of size 3, 1 to 3, I mean, like up to 3. Yeah. So, of course, when you go to the high numbers, and then things become more expensive to check. Because I found some data structures that can supposedly give you a quick check, but you know, when you have already put there a million entities, this check is not so, becomes not so quick, but still it was working pretty well. So I was kind of surprised.
Yeah.
But you know, I think if we didn't mess up and we can extract, at least in principle, core structure, I think it's very interesting because it shows that core guided solver in no way missing anything that heating set solvers are getting. They're getting core structure, that minimum heating set is optimal solution. And core guided doing the same way, but they're not consciously, in a sense, aware of it.
I mean, I would also have other explanations why hitting set might be faster, but that's a different topic, I think. Another question I have is, if I understood correctly, like going a bit on a level deeper than you showed, like you are like relaxing clauses, right? But you might also relax a clause multiple times.
Yes, it's a particular algorithm that does it, the simplest one.
But then I guess you can no longer use an incremental SAT solver, or can you? Because like you actually need to change your clauses now.
Because you go through the relaxations. If you will be going through the strengthening, like if you will be going to the if you restrict formula, you can reuse. But because
yeah, but you don't know beforehand how often you will need to relax a clause, right?
Yes. Well, there are other algorithms now that only introduce one relaxation variable, but it doesn't matter because, in a sense, what they're doing, they, you know, you can. We had other procedure. I showed the simplest one for the relaxation. Yeah. We did the one that does MaxSAT resolution to do the relaxation. But in a sense, it's still, if you carefully look at it, it does relax implicitly clauses multiple times. Not through the introduction of the new variable, but it does happen.
No, and sure, yes, yeah.
But you know, this is a main, I think it's a main problem now of core guided, because you know, look what the core guided is doing. It gets this huge core, right? And let's say we have 2 cores, right? And together they you relax them, and then the new core, maybe it's a join of 2 previous methods, like a huge, gigantic core. But maybe you only need to relax only few clauses from each method. But you don't have a way to do it. Even with the most advanced now core guided solvers, when you relax every clause. Because you kind of don't have access, because if it's inside the meta, it's inside the meta. You don't have a direct access to the clauses in the meta. You can't be careful in the way you relax it. And sometimes this actually introduces a problem. I don't know how to do it more efficiently to be more kind of fine grained in the way you relax. Because you look, this property that I showed before, like you have this cardinality constraint, you have solutions, and you have this meta. So for SAT solver to prove that meta is unsatisfiable core of the new formula, right? That is unsatisfiable subset, it has to go through all solutions and refute all of them. So if you have very poor cores, poor metas, and they may be not minimal. Okay, when the solver works, when you get a meta, usually people try to minimize. I also try to minimize. It helps, but getting to the minimal, it's very expensive.
Yeah.
So basically you do budget. You say, okay, there is a budget, you go, you try. You know, like still, sometimes when cores grow, so it's actually very essential. If you don't use minimization, your solver will choke very quickly because these methods, they grow, and then you are there. But on the other hand, minimization is expensive. And I think there was one paper, I don't remember, like, I think it's would be very cool to be able to kind of, again, look what will help us in the minimization procedure as a standalone problem. You run this solver, you get a meta, it's not minimal. You can do standard, like everyone is doing the standard minimization, greedy-based minimization procedure. You can do a little bit more when you have weights. But again, what from the execution, well, for example, if I know the core structure, that's what I was looking at, but it's with minimization, it does help. So if I know the core structure, underlying core structure, if I extracted it, and now I have to minimize, how it can help me in the minimization, how it will help me to decide which clauses I will next try to, to remove to see whether remaining thing is still a core. I don't know, MaxSAT is quite exciting. Many interesting problems.
So one thing I wanted to keep track of, but I forgot, is like how much of what you said is like, where and how are you using the fact that we're in the unweighted settings? Like, say, suppose I want to be in the weighted setting. Would everything change, or it's just that it would sort of the same, but it would have been more complicated to present?
Okay, wait. Core enumeration is not defined on weight. Enumeration stuff, core and correction set enumeration.
It only makes sense in the.
Yes, for the analysis, course analysis is the same. It will make it different, I guess, if you want to build a new solver and try to get this analysis. Yeah, but here all the result, like for enumeration, it doesn't matter. For optimal solution, you can modify it, MaxSAT, and you'll get it's very simple modification. Basically, when you get a core, this meta in the MaxSAT solvers, so you pick a clause with the smallest weight, and for all others, you split.
Yeah. Okay.
Can show, okay, well, if you want, the last thing I can show you what we did this enhancement with Muses. So, okay, it's actually very tricky to extract this course. So even in theory, it says, okay, consider the solutions and you will get it. Let's consider this problem. So I have 7 clauses, and I have I have 7 clauses and have 1 big core, this green one, and a bunch of small cores, 1 to 6, right? So suppose the first core that I found, first meta is this guy. I relax it. This is what I get. Now, I have 1 cardinality constraint here as well. Because I relax it, I get a cardinality constraint. Now, suppose the next core will be this old big guy. So we find this core, and now we go, if we try to extract cores of original formula, we go through the solution enumeration procedure. So we try, because we only have sum of bi's equals to 1, let's try b2 equals 1. So if b2 equals 1, the rest is 0. So this clause is gone because it's relaxed. Others lost their relaxation variable. Now, you have an unsat core, but this unsat core of original formula, it contains so many cores. Remember how it contains this many cores. So the cores that will get is just a log of minimization procedure. And extracting all of them, it's also expensive. And so what I did, it's a very naive heuristic. Basically, when I was getting these things, I would just randomly shuffle them and minimize. Randomly shuffle is minimize. Again, you can get many cores just by using this very, I don't even describe in the paper, I think it's only an experiment. So you can get a lot of cores of original formula. And another thing that we showed now, that you can actually prove that there are cores that you will never get. So given an execution, this part I really want to make sure that some of the results, it's given an execution, you might have cores of original formula that you will never find using this solution enumeration procedure. So you guarantee that you can't get all the cores, but you guaranteed to get enough cores that give you this core certificate for the optimal solution. So it's something interesting about the execution of MaxSAT.
This is a kind of an interesting example. I was somehow thinking that after one relaxation, your new core is union of two cores or something, but that's like totally false, right? Or I mean, no, it's not for. Oh, it's not for, but it's like it's very hard to. I mean, you're not extract. It's hard to extract it. Yeah. Okay.
So there are many. So I get some unsat guaranteed, right? But if you look back, how many I can get? I can get 5.
Yeah.
But from the solver point of view, I get this subset. I try to minimize. I got 1. I don't know if there are others, or maybe there are no others. But checking it, I could like go and do more exhaustive, like run another solver that does only another enumeration procedure, but was expensive. Simple shuffling and run minimization again. Look, I can't say that we even back 3 years ago, we were not the best in terms of the core enumeration. There are algorithms now even faster. But it's interesting that we can.
But what do you mean when you say shuffling? You mean that you would find some other core first and not this circular one that messed up life for you?
I have C1, C3, C4, C5, C6, C7. After in this solution, B1 equals 1, right? Yeah. So this clause is gone. Others literals are lost. So this is my subset of clauses.
Yeah.
If I give it to minimization, I get a core, maybe C1, C7. But then minimization, all the minimization are greedy algorithm, right?
Oh, so just heuristically, like you say, okay, actually, here's another instance, and you send it to your minimizer, but it's the same. You just sort of shuffled it around a bit.
Yes.
But you didn't tell it.
No, I didn't tell it. I just, because first of all, I do minimization anyway inside the procedure. So, but all the minimization procedures are the same, they're greedy ones. So you remove a core, you remove a clause and say, okay, if it's still unsat, if it's unsat, you try to get from that and solve even smaller core if you can. Mm-hmm. If it's even smaller, so and you keep doing. Yeah. So. Yeah, so this is my dive on MaxSAT and enumeration. And now what we are trying to do to understand even more about
I guess what we would like to do at this point is not to get like all the different small cores, but like get the more powerful constraint out of it instead. Like cores in SAT solving are always clauses.
Yes.
But like when we do pseudo-Boolean stuff, like by the SAT solver, we can get like pseudo-Boolean constraints.
Right.
So in theory, we could get back one pseudo-Boolean constraints from which like all of the cores follow. Like if you have these like activation literals,
right.
Then in your example, you could have like, these are all the cores are binary clauses, right?
Yes, so it's original.
Yeah, or like the later on you had like, I think one was the green stuff and like
no, but this is just show. This is now one big core now. After I relax, I get this is a new core.
Yeah, now you relax, right?
So this is after.
Yeah, oh no, right. You could, yeah, like let's go back to the first picture then, right? But like you can have like I guess 7 times the variable for C1 plus all the other variables greater equals 7. And then you have like one Boolean constraint that like captures all the cores.
Wait, you say we introduce one variable for C1?
You have like just this classical relaxation. It relax everything and like have one variable for every clause.
Okay, yes. From start, okay, you can relax all of them, yes.
And then we could get back like one Boolean constraint that says like
maybe either you write it on the screen.
Yeah, because I don't write with mouse.
Do I need to stop sharing or
no, you can. I can write on your screen, I think.
Okay.
But I need to get my pen connected so I can write. I mean, the problem is I'm not sure if that's actually something our solver would actually happen to do, but and then I should be able to annotate. All right, let's just call these like, oh, wait, why is it drawing in white? I guess black is easier to see than white.
Sometimes, depends on the background.
So if like, we have Y variables for relaxation, and like Y1 for C1 and so on, right? So I guess we could have like 7 Y1 plus I from 2 to, what do we have, 7? It's greater equals 7. Like this is like kind of a one Boolean constraint that like covers all of these binary cores that are blue.
Are you sure you don't mean 6 when you write 7?
Yeah, I think I mean 6 and write 7.
So wait, let me understand. So you so what this constraint says? It says that if it's 1.
It says either I need to relax, like I need to like I guess my hitting set either has to like hit this one, or it has to hit all of the other, right?
Right. Yeah. So wait. Either hitting set will be always of size 2, right? Because there's a circle core. So if you only hit C1, you will not hit the circle.
Yeah. I ignored the outer core. I guess now. Okay. I just looked at the.
Yes. Okay. Then I understand.
So the best possible, I guess, would be that you change Y1 to a. No, I mean, wait.
I mean, you could probably just have a 7.
You could change Y1 to a 5 or something.
No, I think like, no, but just having a 6 here and a 7 here, maybe.
Wait. Then
this could also cover the outer one. It's definitely no, I might need this.
No, you're
7
messing up because you're forcing Y1 to always be true, right? So I think you really meant 5 and 6. I mean, this has
many.
The slack of this guy is 5, Stefan. So Y1 always propagates.
You like this one better? I mean, what you
like
can do.
5-6-1 better, but
no. The reason why I want the 2 here is what you can essentially do is you take all the clauses we have and add them together, and that's exactly the constraint you would get.
Okay.
Right, like we have one clause that has like all the author variables. This gives us like one of these y's, and then we have like all the clauses for the blue stuff we had before. So this gives us this constraint. Except that now I don't think that the other direction worked anymore. Like before, when we just considered the blue stuff, you could also go back. You could go from the pseudo-Boolean constraint to all the clauses that correspond to cores. I think now this is no longer the case.
Wait, but can I ask you about this cardinality pseudo-Boolean constraint? You can divide, because everything is integer, you divide by 2 and you round. It will be the same. Right?
Yes, actually that's true.
So you'll have 3y1 plus.
But you probably want to multiply it by something before rounding. No.
No, why do you do this?
Oh, right. So what? So.
But we still have a lot of them here. So. I mean, I like it a bit more, but you still can't get all the clauses back now, I think.
Okay, let me understand, even if you look at your first one. So the first one says that if, let's say if y1 is 0, then you need to have at least 4 i's somewhere between, but it will not.
I mean, yeah, I mean, this is why I'm not sure I like this one super much. Like the one before, that's the weird thing. Like sometimes you can combine cores together without losing anything, and sometimes you will lose stuff, right? So, in this,
but even if 6,
like,
let's say
for this one, I claim we don't lose anything. This like describes all the blue stuff.
Yes, so it says if a middle is 0, then all outer has to be 1. And if at least of them is outer is 0, then y1 has to be 1. Yes, it's a good, but you see, to write this constraint, you need to know the core structure.
Yeah. Yeah, but I think essentially like the hope that we have is that the pseudo-Boolean solver magically gives us back this constraint.
I see.
Instead of like I mean, the SAT solver might give you back like the clause that has all of these variables, and maybe we happen to get something better back.
But even from MaxSAT,
but it's very, very like hand wavy.
You know, this is from MaxSAT solver point of view. Let's say I have some at some point of the search. This is what we are looking with Nikolai actually now. So if I'm at some point of the search and I have this very complicated cardinality constraint is simple, just cardinality constraint, but the structure becomes more and more complicated. Now, suppose we stop and we look at the core structure, we can extract it. Can we rewrite? Like what you wrote, it's maybe one way to rewrite, right? So because we already know a lot, and on top of it, we extracted the core structure. Suppose. And it's not arbitrary core structure, the core structure is related to this cardinality constraint. So the question is how to rewrite. Maybe like aggregation or, one very simple thing. Like, remember I was somehow mentioning multiple times that depends on the execution. And you can have like if we go back like this example that I showed very earlier, it's actually an example that we are using. But look, if I go through the procedure that I showed here, it's not the best execution, But like, look, there are two green cores. If I would find two green cores and one small blue core, I will be done because it's a 3 disjoint cores. You see how execution matters. It matters a lot. It's a simple case, it's a disjoint course, but in any case, like if I start doing something and I see that I'm stuck, if I can go back and find disjoint core and maybe restart, starting from this disjoint course or disjoint kind of what we call the transitive closure. Like if you have disjoint transitive closures, like groups of cores, it will be much better because you might, even without aggregation constraints that you mentioned, just even rewriting it will be, it will reduce search space over this cardinality constraint. But what you're suggesting, I think it's even more powerful because it relaxes. It's kind of a shortcut. Wait, look, let's maybe go again to understand what it can be used for. Right, so how the what's a good execution of the solver? First, we will find C1, C2, for example, this guy. First, I find this is a small core. It's easy. So this is the first I found. I will relax it. And then if I find, then I need to find the big one, right? This is the only way I can get there because there's not too much difference here. But sometimes there is a big difference in which order you find. But suppose now I know the core structure and this is a part of the problem and I ask you to relax. So how would we do it? We introduce these y variables. We throw away everything that we had before, right? When we just run MaxSAT on this subproblem, we'll have two cardinality constraints. The first one, maybe relax the big core and then the small one. So now suppose we stop, we throw away our cardinality constraint, I still want to do the relaxation. So I want to introduce this y variables that you suggested and add this constraint. We have to add equality, right? If we want to do the relaxation, we have to add, use it as a relaxation constraint. It has to be equality. And add it to the solver.
I mean, if you like do this as you described it with the equalities, I guess maybe.
Well, let me think. So,
I mean, like the success solvers I look at, like just rewrite the objective function, and then like I mean, I guess you.
I think what we're doing is called this OLL method or something. This is what we implemented. So you would get equality by adding.
Yeah, but you add like set variables.
I know OLL is very similar to this RC2 algorithms. I know it pretty well. You add constraints as soft, right? You add cardinality constraints as soft constraints.
So incidentally, that's like another thing that I wanted to ask about earlier. So the way we implemented core guided search is that we rewrite the objective function, and then what we learned, I guess, turns into a new constraint. I mean, how you said that you can deal with, you can treat the cardinality constraint as soft or hard. Like, what's the, how does this affect?
So look, I don't know. I didn't look at this soft relaxation constraint. How does this affect? No, enumeration. No, I didn't look at it in the very much into details, because I first want to look at what the algorithms we have, like how it affects. But wait, it doesn't matter. Okay, you use whether you use soft or hard cardinality constraint. But if to do this analysis, when you stop, you look at all the soft constraints that when you run the solver, you treat all the soft constraints, including the soft constraints, the cardinality constraints, as hard constraints, right? The only thing that you might have higher weights, right? Because you, if you have something inside, you push weight of soft cardinality constraints, you push weights up. Yeah, I need to look at it. I don't know. It might change the analysis.
Another thing that you mentioned, I just got curious because I think this is something that we didn't really look into, is when you're doing core guided search, I understood that it's, and you find a core, like is it very important to try to minimize it? I mean, otherwise you're getting huge cores after a while. Yes. Because I think this is something that we didn't really look at.
Yeah.
Definitely helps putting a budget and run, because this will kill you very quickly. Because a lot of, from what I observed in the beginning, it's very easy to minimize. Like when you start minimization, sometimes SAT solvers somehow are very bad in returning the cores. They're gigantic. This methods that we are getting, they're much bigger than the minimal, at least some of the minimal. So even with a very small budget that you put to run the SAT solver for the minimization, you can trim a lot.
I'm thinking that maybe I would love for this discussion to continue, but I'm thinking that maybe we should conclude the official part, and like, thank you for a wonderful seminar and already very interesting discussions. So thank you so much.